Welcome to week 11 of microprocessors and robotics. We're going to shift our focus to robotics. And this week we're going to be taking a look at servo and stepper motors, kind of the history of robotics, the different types of robots, how we define robotics, and some different environments that we would find robots in. Our first topic that we're going to tackle is servo and stepper motors. You might be wondering why these are important. Well, when we talk about robots, something has to drive the motion. Something has to be powering that movement. And so motors are what does that. So we have two main types. The first one is a servo motor. So servo motors are what we call a closed loop system. This means that they're continually receiving feedback on where they're at position-wise. So instead of the controller telling the motor to move X, and you just trust in good faith that the motor has moved X amount, the closed loop system provides that feedback to confirm, okay, yes, the motor has moved the proper amount that it was told to move. So that's a closed loop system, and that's what servo motors run off of. So this feedback is what controls the motion and the end position. So it's constantly giving feedback on what position the motor is at. And this is usually communicated by an encoder. So it does a little bit of encoding, obviously, and the optical encoder is always watching the number of rotations and the position of the shaft to figure out where the motor is at. Another point to note on servo motors is that they do require complex control modules usually, and this should make sense because of that closed loop. There's more components within that loop. So instead of just telling the motor to move and it moves, there's that continuous feedback loop that you need more pieces for that to run. Here to help us understand how servo motors work a little bit better, I've outlined some basic steps of operation for these. So the first step is that an input will kick off the motor movement, right? So there's going to be a signal coming from somewhere that lets the motor know it needs to move. And the motor position is going to be continuously measured as it moves. And that encoder that we just talked about is providing feedback on the position. It's giving information back into that loop on where the motor is so that it can make adjustments as it goes. I jumped ahead of myself a little bit there if I would stick to the steps. So 4, that measured position is compared to the command position. So it's almost like a subtraction routine, right? So that encoder is giving feedback on where the motor's at, and then it's doing a check. It's saying, okay, does where the motor's at match where it should be? No, we need to move it this much more. So there's that continuous feedback loop there. If there is a difference, then an error signal can move the motor enough to reduce that difference. So if the motor is not going to the endpoint that you want, sometimes it can correct enough to get close enough, and then it will check again, right? So the encoder is continually checks to see if the motor is where it should be. If it's still not, it'll do a self-adjustment again. And so this continues on and on until step 6, when the error signal is 0. So that's when the motor is exactly where it should be. So it's kind of the typical operation of a servo motor. There's a lot of great advantages to a servo motor. Here we'll look at some of those advantages and the disadvantages. So the first advantage is that it's great for high speed, high torque operations. So when you need a motor to control something very quickly, or when you need something that's very powerful to provide a high degree of torque, a servo motor is great for that. And then you see the second bullet point, it can also maintain that torque at high speed. So not only is it high speed and high torque, it can be both of those at the same time. So that's something important to think about as we consider all of our robotic variables and our motors and things like that. Something could be good at different things, but it's also important to consider what can it do simultaneously. So just because a motor has high speed and has high torque, that doesn't mean it has them at the same time. You could get into a case where at high speeds the torque is really low, or to get that high torque it might have to move at a really slow speed. So just keep in mind some of those trade-offs that could be present. But here, for the purpose of this discussion, servo motors in general can maintain their high torque at high speeds. That's a huge advantage to them. They're also more efficient, so between 80 and 90% efficiency, which is really great. They're quiet, so they're not creating a lot of excess noise, and you can also get them in AC and DC power options. So there's some flexibility there with a servo motor. This does come with a few disadvantages, right? We can't have everything. So the first is that the circuitry is a lot more complex. Hopefully this makes sense, right? We have that closed loop that's making things complex, and then they're just functioning really efficiently, right? They're very quiet. You have AC and DC options. So all of this results in circuitry that's a lot more complex. Understandably so, this makes them more expensive because they're such a great motor option. And then sometimes they require an additional component called a gearbox if you're going to be running them at lower speeds all the time. So those are just things to think about when you're considering a servo motor. So the second of these two main types of motors is the stepper motor. And a couple quick things about stepper motors. They don't have brushes. The rotation is divided into equal steps on these, and that'll become a little bit clearer momentarily, I think. But so the rotation of the motor is divided into equal steps, and each of those steps is very precise. So because of that, it doesn't use a closed loop system. It can get away with an open loop system. So what that means is that there's no feedback on the position. So there's no continual check to see if the motor is in the right place or if it's made the appropriate number of turns. There's just good faith that because of those precise equal rotation steps, that the motor is where it should be. So that brings me to the second to last bullet point, right? The motor's position is just achieved by a command for the motor to go to a particular step. So there's no check. There's no confirmation of that. It's just told to go to a step, and presumably that's what happens. And then the way the motor is getting to each step is that pulses are being sent to the motor for each step that it needs to take. Before I cover a stepper motor's advantages and disadvantages, you'll note that I didn't step through the operational steps of a stepper motor like I did with the servo, and that's because that's a lot simpler without that open loop system, or I'm sorry, without that closed loop system. So a stepper motor is using an open loop system. Essentially, it gets the command, pulses are being sent to the motor, and for each pulse, the motor is moving a certain amount. And because that's so precise, again, we trust that it ends up where it's supposed to. So the steps, the way it's executing the function or the movement is a lot simpler. So some of the advantages to this, what I just explained, the drive control is a lot easier on a stepper motor. The torque, it can also be more constant. So instead of possibly tapering off, you end up with a much straighter and constant torque. Using these, you don't really need to monitor a stepper motor. That's why we can get away with an open loop system, and they're much more affordable because there's a lot less going on with them. So stepper motors can be a very simple and very reliable motor for certain applications. The disadvantages to these, though, are that these motors don't have any reserve power, so servos, some of them have that. There's also high torque losses at maximum speed. So for the most part, right, this may sound contradictory to the advantages, but these two things are kind of happening at the same time. So the advantage is you have constant torque up to a certain point, but then you can really experience high torque losses once you get beyond that at your max speed. Part of this, or this is what partially contributes to the need to accelerate slowly, so you can't just activate these motors very quickly and have them move very quickly. You have to slowly ramp up to the acceleration that you need, and they are prone to more vibration and noise. So here's a quick comparison of servo versus stepper motors. We talked extensively about the closed loop that a servo has, whereas a stepper has an open loop system. The servo loop is controlled with continuous feedback. It uses that closed loop system as part of its control, whereas a stepper motor is controlled with pulses. So again, it's just pulsing to send the motor to a certain point. And then we didn't get too far into this, but it is kind of an important note. Servo motors, they typically have 4 to 12 poles, whereas a stepper has a lot more. It has 50 to 100. So there's not necessarily, one of these is not better than the other. These are the two main types of motors that you'll commonly encounter, and they're just good for different applications. So depending on what sort of speed, what sort of torque you need, if you need a quiet application, if there's a lot of vibration going on, there's a lot of different variables that come into play when you're selecting a motor. And depending on the environment, what it's being used for, some applications, a servo motor might be better. You might need that really high precision and that really high torque or that high speed. And in other cases, a simpler stepper motor might work just fine. So if you don't have a lot of vibrations in your environment, you don't need to accelerate very quickly, a little bit of noise isn't an issue, then a stepper motor might absolutely be appropriate for that application. There's certainly within these two types different degrees of what do I want to say, different options, right? So you can have a really premium servo motor, and then you can have a really basic servo motor, right? And same thing with the stepper. So one is not necessarily better than the other. Again, there's kind of different tiers within each of these, and it's just selecting the best motor for your application. So now we're going to move on to the definition of robotics. We're going to look specifically at what it is. I'm sure most of you already have an idea in your mind of what robotics is. Typically in an in-person class, I would ask for a couple examples. Here, I would just kind of ask that maybe you take a minute and cement in your mind, maybe even jot down an answer. What do you think robotics is? So we define a robot as a machine capable of carrying out a complex series of actions, especially one that can be programmed by a computer. So this is a very basic definition. There's a lot of different kinds of robots, a lot of different applications for robots. This definition encompasses a huge variety. So it has to stay kind of simple to encompass all of that. But I think this does a great job of kind of summing up what we mean when we're talking about robotics. So we're talking about machines. They're carrying out a series of complex actions. They're going to do this automatically, and typically we can program them using a computer. I want to pause for a second in this lecture and have you jot down a number to this question. How old do you think robots are? So give this some thought if you need to. Take a couple of moments, no Googling, jot down a number, and then we'll go over to the discussion forum. I'll have a forum set up for this week, and go ahead and make your post with your number on how old that you initially guessed robots are. So it's a little bit harder to get everyone involved, unfortunately, in an online class like this. Typically in class, we would get a guess from everyone, write down all those numbers, and it's always really interesting to see the wide range of guesses from students. So we'll try to replicate that here. We'll see how it goes. So before we go any further, make sure you pause if you need a second, write down that number, write down your guess, and then it doesn't have to be now, but at some point this week, take that number over to the discussion forum and just make a simple post letting us know what your initial guess was for this question. We'll take a look at some of the key points in the history of robotics, but to answer the question that I just posed to you, robots actually potentially date back as far as 77 to 100 BC. So that's 2,000 years ago. Actually, there was a device called the Antikythera that was found in Greece about 100 years ago. And this device was made up of several gears. The theory is that it could potentially be a mechanical computer that was used to calculate the position of maybe the sun, the moon, some of the planets. And so based on some input to this machine, it was thought that it would then calculate the position of one of these bodies. So that's the thought. We do know that between around 278 and 212 BC, this is actually a little bit before what we think was the start of robotics, but there was Archimedes who didn't invent robots per se, but he did come up with a lot of different mechanical systems that we use in robots. So he wasn't designing robots. This was still before even the Antikythera device was thought to date back to in Greece, but Archimedes did come up with a lot of basic mechanical systems or even some more complex mechanical systems that have formed a foundation for robotics, and we use some of these today. Further supporting the theory that robotics has been around for at least 2,000 years, the hero of Alexandria, who was an engineer, a mathematician, a physicist, he wrote a book titled Automata back somewhere between 10 to 70 AD, so about 2,000 years ago. And this book contained a collection of all of these different mechanical devices that were used in temples. Which is really interesting that that's where they were applying these mechanical sort of robotic, primitive robotic machines. It's also said that the hero of Alexandria designed an odometer. So this would have measured the distance that back then it would have been a cart, right? Today we use odometers in our cars. But this was kind of laying, again, the foundation for what we know as modern robots to follow. It's also considered that the Heliopile was one of his inventions that the hero of Alexandria created, and this laid the base, more conceivably, for the modern steam engine. So instead of just, this isn't just kind of abstract concepts of robotics, these are the very real foundations of robotics that were happening 2,000 years ago. So we have collections of different mechanical devices, we have odometers calculating how far things are traveling. We have essentially a foundation for steam engines, all of this being conceived and created in rudimentary designs between 10 and 70 AD. I won't go through every detail of the history of robotics in painstaking detail. I do just want to cover some of the key highlights so that we can see how robotics have progressed over the past several hundred years. So we're going to skip ahead considerably. We've kind of seen the foundations of robotics, how they were thinking of these things thousands of years ago. So we'll go ahead and skip forward to 1495 or thereabouts, when Leonardo da Vinci was around. So Leonardo da Vinci was a man of the Renaissance. He had a lot of different interests. Invention was one of these. He's renowned for some of his inventions during the Renaissance period, drawing, painting, sculptures. He was very artistic and also very mathematical and science-minded. So he had a broad variety of interests. It's said or thought that he did design the first humanoid robot, so to speak. So he's come up with designs for this. It's not known if it was ever actually produced. More than likely, it was not, but he was thinking about these things. So there were already conceptions of robots as early as the 1495s, or even in the 15th century. Shortly after that, in 1645, we have a much more concrete example, so something beyond drawings, something a little more complex than an odometer. Around 1645, Blaise Pascal invented a calculating machine. So his father did taxes, was most likely an accountant, and there were only 50 of these built, but you can still find some of these in museums today. So this machine helped calculate and was essentially a rudimentary calculator. So it can be thought of as a very early robot, right? This is the machine. It's performing a set of potentially complex tasks for the time. Obviously, it wasn't programmed using a computer, but that's not necessarily a requirement for a robot. So this can kind of be considered one of the early concrete examples of a robot or of a machine performing tasks, these mechanical tasks for humans. And then we see in the 19th century and the 20th century the development of robotics really starting to pick up. So in the 1800s, Joseph Marie Jacquard invented a loom that could be programmed to create designs to print onto cloth. In 1921, the term robot was first used by a Czech writer. And this, it was actually not used as a scientific term by scientists, but it was in a play where the plot was about a man making a robot to replace him. So people were forming their ideas and their conceptions about robots. Um, Even then in 1921. So a little bit later, 1937, 1938, not so very long ago, the Electro robot was created, very human-like. It could walk and talk and even smoke. That kind of says a little bit about that time period, that was one of the activities that it did. And so this was a big deal. This robot was created and then it was unveiled at the World's Fair. So it was a big deal. It's such a big deal, you know, that they took it to the World Fair, they unveiled it for thousands and thousands of people. And so this is kind of a huge mark of the development of robotics in history. Moving on, we have a couple more notable highlights. You'll see that the timestamps for these are getting closer and closer, so we're really starting to gain momentum in the 20th century. In 1942, there was a programmable paint sprayer designed, and then shortly after that, in 1954, George Devol designed what we refer to as the first truly programmable robot, and then went on to form, in conjunction with his partner Joseph Engelberger, the world's first robotic company, Unimation, standing for Universal Automation. So George Devol designed the first robot, but his partner actually got some more of the credit for this, and Engelberger has been called the father of robotics. Several more developments. So 1957, the Soviet Union launched Sputnik 1. That's when we started to get into satellites. We're starting to look at space travel, and of course, robots play a huge part in that. In the 1960s, robots were involved in a candy factory, so they're starting to be used for industrial automation. MIT, Stanford started a artificial intelligence research laboratory in 1964. So it's really picking up. The universities are dedicating their time and resources to this. 1965, we see another university. The Robotics Institute is established. So all of the world's greatest minds are being applied to this topic, so that its limits can really be pushed and that we can really or could really see to what extent robotics could be used in our lives. We have a couple more developments here. We have the Stanford arm, the electrically powered computer-controlled robot arm. So we're getting a little bit more precise now with the types of robots being developed. 1973, there was a full-scale anthropomorphic robot created. The limbs could be controlled. It could essentially have, it had functioning vision. It could hold a conversation. And of note, it was thought to have the mental ability of an 18-month-old child. So we're getting more and more complex as we go on. You'll see even from 1965, when we had the Stanford arm, to 6 years later in 1975, Victor Shenman developed the programmable universal manipulation arm, which is widely used in industrial operations today. It was then, and the basis of that design is used even today. So you can see the progression very quickly, even in a matter of less than 10 years, from a very basic robotic arm to something that is much more complex. Wrapping up the history here, 1997, NASA's Pathfinder landed on Mars. So again, robotics highly involved and used for space travel and exploration. 1998, some of you may remember this. Kismet was created. This was a robotic creature that could interact emotionally, essentially, with people, or in kind of a replica of emotional interaction. 1999, Sony released the first robotic dog. So the note here is that now robots are not only being used for industrial automation, for space exploration, but they're becoming so common that they're finding their way into children's toys. And I'm sure, even today we see robotics involved in so many things, and so many toys, right? It's expanded from a simple robotic dog, to all sorts of things. So our last thing of note, in 2001, the iRobot PackBots actually searched through the rubble of the World Trade Center after 9/11. So as they were processing all of the rubble and the aftermath, the robots could actually be used to search through and for retrieval. And they've actually since then been used in different military applications, and things like that. So we're becoming more and more advanced. We're finding more and more applications for robotics. And in conjunction with this module, I'm not going to play all of the videos here, but I will go ahead and post some links to different videos with some updates of kind of where robotics are today. Okay, now that we've seen how robots have developed through history, there'll be some videos with kind of some updates of where they're at now posted. Let's take a look at the different environments that robots can be used at. So we kind of saw the evolution for them being used almost uh, as a novelty, right, on display at like the World Fair, to very practical purposes, space exploration, and industrial applications, and then to being used in things as simple as children's toys. So some of the environments today that robots are commonly found in, we have industrial environments, different factories, typically service environments, space exploration, of course. We've talked about that a little bit. Domestic environments, so think about how complex even kitchen appliances are becoming. The military uses robots for a variety of things. Hobbyists are building their own robots now. There's different competitions. Medical fields can use robots to perform surgeries even now. They're playing a part in those. And then we're also using robots for our own entertainment. So there's a huge variety of applications here, and we'll look at a couple of these more in depth. So probably one of the most common uses for robots are in an industrial setting or a manufacturing environment. Here, an articulated arm robot is very common. They're used to do things like welding, painting. In the top right, you can see one is doing some machining. So any set of repetitive tasks that may fatigue a human very easily or be very difficult to perform very quickly, we can outsource a lot of these movements and these functions with robots that are a lot more reliable, and a lot more efficient. Then we have domestic robots for home environments. So these are usually done to take over chores that we would typically find not necessarily repetitive or sometimes not even difficult, but just unpleasant. Some of these could be considered difficult, or for things that we can't do, such as surveillance. So different surveillance systems in the home can be considered, they're using robotics. So we have pool cleaners, we have some gutter cleaners, we have, of course, the iRobot vacuum, right? That's a huge one. I didn't add it to here, but of course, Alexa or some form of that, Google Home, those are all really big right now. And so domestic robots are becoming increasingly more common in the variety and in what they're doing, and just how powerful they are. Then, as I briefly mentioned earlier, we're also using robots in the medical field. So in some different environments, sometimes they are solely performing surgery, sometimes they are simply assisting a surgeon with surgery on a much more basic level, depending on the application. But you can see here, this looks to be quite a complex robot that is performing a surgery with a surgeon supervising. So this is a very incredible advancement. It's potentially a lot more precise, right? There's no risk of a hand slipping or anything like that. And so for some of these more basic surgeries, medical robots can be used. The military has also been using robots for a very long time for a variety of tasks. These are really great so that we can minimize the amount of risk to humans when we're undertaking certain tasks. So they're typically performing support applications. They can be used for things like bomb disposal, reconnaissance, law enforcement, search and rescue. You can kind of see some different examples here, especially some of the search and rescue robots. There's almost like a little mini tank here or a defense unit. Different attachments here, so they can be used for a lot of different applications as well, so that we are not placing human lives in danger. And then we come to the entertainment robot category. So you might have seen some of these little gadgets, or you can think of dozens and dozens of other little robotic gadgets that you've seen. There's kind of the novelty category of things that aren't really necessary, but they're just fun to have, like maybe a robotic alarm clock. Toys is a great example. It's a very common one. I'm sure most of us have some sort of little robotic toy or gadget in our home, especially if you have children. And then there's hobbyists as well that spend a lot of time designing and developing robots for different things. So it could be robot battles to perform specific tasks. There are robotic competitions, things like that. So we're seeing robots find their way into even our daily entertainment. And the last application that we're going to look at with a little bit more detail is robots for space applications. So they can be used for space exploration, different scientific experiments conducted in space, and even for just monitoring certain environments in space. We're able to use robots to collect data, to retrieve pieces of the environment and things like that, so that we're not having to constantly send human beings out into space or out into that environment. These space robots are a great way to supplement the efforts of our astronauts, and we can gain even more information, gather even more data, and increase our knowledge of space by using these robots. Now that we've looked at some applications of robots, we're going to take a look at the main different types of robots. These types you can usually differentiate really easily in industrial applications, but they're essentially used everywhere. You'll just see probably the largest variety in an industrial application. So for all applications, we have articulated robots, there are Cartesian robots, cylindrical, polar, SCARA, and Delta. So we'll take a look in a little bit more detail about what each of those types means and essentially what it is and what the difference is between types. The first type of robot that we'll look at is the articulated robot. So you can see there's a lot of different joints on this robot. It has a really good range of motion. Typically, there are anywhere from at least 2 joints to potentially more than 10. At the base, there is usually a twisting connection. So you can see at the bottom where it says arm sweep. That's typically a twisting joint. And then the other joints are a rotary connection. So each joint we refer to as an axis, and there are commonly 4 to 6 axes within a robot. So you can see on this robot we have our 1 at the base, arm sweep is 1, the shoulder swivel is 2, our elbow is 3, we have a pitch, yaw, and roll at the end, which gives us another 3. And so this robot has 6 axes on it. And so these all combined together, this range of motion here will allow us to create a very wide and large work envelope for this robot. So you can see it has a lot of degrees of motion, and it can probably very precisely get to a specific position. So there's a lot of there is a lot of flexibility with these articulated robots, and that's why you'll commonly see them in industrial applications when you really need to get into a specific spot, or the robot needs to move across, like if it's spray painting something, and in a smooth, consistent motion. An articulated robot can be really good for that. Or if it's having to navigate into a really tight spot, think like maybe welding in an automotive application. An articulated robot would be really good for this because of the range of freedom that it has. The second type of robot, the Cartesian robot, is much more simpler than the articulated. Sometimes these are called gantry robots. So you can see in this image, these have 3 linear joints, so they don't rotate, they just move back and forth. So in a Cartesian robot, there are always 3 joints, they're linear, they're moving back and forth. And they're called Cartesian robots most of the time because they're using the Cartesian coordinate system. So a lot of you might be familiar with this, especially if you've gone through geometry or if you've done any sort of machining. There is an X, Y, and Z plane to these. And so just using those X, Y, and Z planes, this robot can move back and forth in a linear fashion. Now we can add another degree of freedom to this robot by attaching a rotating wrist at the end. So that would be right here. We could potentially add a rotating wrist to add a little bit more flexibility here. And then just to give you an idea, for example, this would be the Y plane, this would be X, and this would be Z. So we could give the robot a set of X, Y, and Z coordinates, and it could very quickly and simply move to that location. So this little box is essentially the work envelope that we're dealing with, and these can be really good for very simple linear tasks. Our next type of robot is a cylindrical robot, and you might notice there's a lot of cylinders involved with the construction of this robot. So cylindrical robots will typically have one rotary joint at the base, and so we can see this right here. This arm is able to twist back and forth, and it has at least one prismatic joint collecting the links. So a prismatic joint essentially allows us to rotate and to move up and down. So you can see this arm right here is rotating like we first highlighted, but it also has the freedom to move up and down. And then we see the same thing over here. So this little cylinder probably is able to do a rotation here, and it can also move up and down. So that's another prismatic joint. And these types of robots have a cylindrical work envelope, so you can imagine if all of these joints were extended straight out, that would be as far as the reach would be. And then of course, because the base is connected in a rotary joint, we would have a rotary kind of a circular envelope here. And then we would be able to move up and down within this circular envelope. And you can see link 4 here, it has an end effector attached. So this could be a variety of things. It doesn't necessarily have to be kind of this clamp. But everything else excluding this clamp is a good example of a typical cylindrical robot. The next type of robot is a polar robot. So this is a little similar to the cylindrical robot, which essentially had a cylindrical work envelope. The polar robot has a little bit more of a spherical work envelope. So it doesn't have to come straight out. You'll see here it has this angle degree of motion, and so that gives it this cylindrical shape. It doesn't just have to move up and down, it's able to pivot on an angle, and so that gives it a little bit more freedom. This one we can see is a little bit stiff, So you don't have kind of this whole inner area. You have a very constrained work envelope, so this arm can move in and out to an extent. So in a polar robot, the arm is usually connected to the base with a twisting joint. So this arm probably rotates around. We see this little box here rotates around and can also move up and down at an angle. And so this combination of two rotary joints and a linear joint are what gives us this unique spherical shape. And these polar robots typically use what we call a polar coordinate system. You might have heard of this in one of your mechanical engineering classes. If you're a mechanical engineer, it's easier to use a polar coordinate system on this because the work envelope is more sphere-like. And so because of that, sometimes these are called polar robots and sometimes these are just referred to as spherical robots because of the work envelope that they create. Our fifth robot is the SCARA or SCARA robot. This might look a little similar to the cylindrical robot that we looked at, but it doesn't have as much freedom on the X and Y axes. So you can see right on our cylindrical axis, this probably would have been able to move up and down, or we would have some sort of up and down linear motion here. But we don't. We only have that motion in one spot on this little end effector here. So this can move up and down, but nothing else can, which makes the work envelope a little bit smaller. But these are typically used for very specific tasks. We can see that these have two parallel joints. So we have one here and one here. And these are commonly used in assembly applications for very simple assembly applications. We don't need a huge up and down or y-axis envelope if we need something that's a little bit more concentrated. And we just need a very simple robot. You can see this only has the two parallel joints. It has 1, 2, 3 rotary joints. This is a limited range of motion, but it's typically enough motion for an assembly application. And so this very specific type is just simply called a SCARA robot. The sixth and final type of robot that will wrap up our robotics discussion for this week is the Delta robot. So this is a little bit spider-like, if you will, in the way that it looks and moves. And it's made from jointed parallelogram. So we have a triangle up here and a triangle down here. And so these are connected together by a very unique means of connection. And the way that this is connected, it gives the robot essentially a dome shape work envelope, if you can imagine that. And because everything is controlled so precisely, if you think about it, this little end spot here is controlled by 3 different arms, so it can be very precisely moved. You're not just relying on one arm, but you have the preciseness and the support and the structure of all 3. And so you can perform really precise and delicate movements with this type of robot. And because of that, this is commonly used in food applications, pharmaceutical applications, and electronics where we need that level of precision. And so this is really good for those specific applications. It can also be used in others, but that's typically where we would find these when we need that level of steadiness and precision.
This is essentially the second phase of your project. And in this phase, you'll be working on researching the top ideas that you've brainstormed. So in the last phase, you should have picked your top ideas, the top few. So now you're going to dig into those ideas a little bit deeper. You're going to research them. Based on your research, you're going to pick a final idea as your project. And then after you have your project selected, you're going to assess the potential risks, develop a timeline, and determine what components you need for this. And so the point of this is to mimic a real-life project in some aspects. Typically, you don't just get to dive into a project, you have to do usually some sort of risk assessment. Sometimes it's formal, sometimes it's really informal, but you should always be thinking about the risks involved, what could go wrong. And by doing that, you can help think ahead and mitigate those For almost every project you have, if not every single project, you'll need to develop a timeline. And this helps you to be able to stay on track, and so you can kind of see where you are and if you're going to meet your ultimate deliverable date or not. And then, of course, you'll need to determine what components you need for your project. That way, you can make sure that they're available to you, or you can find a way to make them available. So I mentioned researching your ideas. So ideally in your brainstorming, you've come up with a couple ideas. You may not know how to make them work with a microcontroller or code yet, but you have an idea that you think could work. So researching helps to flesh that idea out a little bit more. So that way you can tell if your idea includes some really complex coding that we might not get into in this course. That might not be a great project, or if the code is extremely simple, that might not be a suitable project. So when you research, you get a better feel for what's involved in this project, what kind of coding skills you need, what kind of circuit building skills you need, so you get a comprehensive view. There's a couple different ways to research. One way you can do this is to pick a piece of your project. So if your project involves a temperature sensor, for example, a temperature sensor would sense the room temperature, and if it's between two values that the user inputs, if it's between 70 and 80 degrees in the room, a green LED could light up. If it's outside of that range, a red LED. And of course, these could signal things like heating and cooling systems. So maybe if it's over 80, you could power a small fan, something like that. So anyways, the piece of the project that you would want to focus on is the temperature sensor and figuring out how to make that work. And so that's what you would be researching, is what's involved in programming a temperature sensor in C. So when you're doing this, you can look for similar projects. You cannot copy projects step by step, but you can certainly look for projects that are similar to yours, and you can pull ideas from those. So I mentioned the LED, you could connect some LEDs to a temperature sensor to give you an output. If you found a project that did that, the way you could adapt that, like I said, is to connect a fan or to connect something else. So you're modifying an existing project a little bit. So similar projects are really good sources of inspiration. They can really be good tools to show you kind of how to lay out the code, the steps that you need to go through, and maybe what's involved for a specific sensor. Because specific sensors can involve code that is outside of the scope of what we're learning in this course. But it's not necessarily difficult. You just have to figure out your inputs and outputs and occasionally a couple extra commands, which is totally doable and which I absolutely encourage. That's the point of this project, is for you to do a little bit of independent exploration into commands and figure out what else you can do with C. Something else you could do is figure out an identical project to what you were thinking. So if you come up with an idea, you find somebody's already done it, don't just copy them step by step, but figure out how you can improve upon that idea. So how can you go that extra mile? What else can you incorporate? How can you make it a little bit more difficult to demonstrate that you're understanding the material and you're able to take these concepts and apply them? So there's a lot of different things that you can look for in your research. I fully encourage you to find out everything you can about your idea, what components are needed, who's done it before, what does the coding look like, and things like that. I do just have a couple rules for when you're conducting your research. So you can absolutely find and modify an existing code. So years ago, there was a program where there was like a little knocking code activated by a piezo buzzer. So some students took that from online and they modified the code to kind of their own little song, their own little knocking code, and they changed the inputs and things like that. So you can kind of use a code structure and framework, but you can't copy the code exactly. You should be doing some sort of modification. And that doesn't just mean modifying the outputs to be a different pin. It should be a significant modification. And if you're not sure what a significant modification is, or if something's borderline, absolutely send me an email or comment in your group discussion. I'll be keeping an eye on those. If you are worried that you might be copying something too much, or if you're worried about what modifications might be needed. So it's certainly okay to use a reference code. That's absolutely fine. You just can't copy it. And the same thing goes for circuit designs. So we're focused on microcontrollers and robotics here, not necessarily on circuit construction. I think it's very important that you be able to construct a basic circuit. That's why we've built a couple so far. We will build more as this course goes on. But to help you in your project, you can absolutely find a circuit schematic that looks close and use that as a reference to build your own circuit and to get things connected in the proper way. Because again, with some of these sensors, they have multiple pins or multiple inputs and outputs, so you might need some help on how to connect those and what all needs to go together there. So certainly look for examples of circuit designs too, and use them as a reference. Essentially, you can use anything as a reference, just make sure that you're crediting it, and so cite it in some way, and do not copy it exactly. That's essentially the main guidelines for your research. And so I've included a link in this presentation from a site where they're taking a base code and they're modifying it for a different purpose, essentially. So this is a really good example of taking a code and making some modifications to suit a little bit of a different purpose. And so I think this is a good guideline for kind of the type of modifications and the extent that at a bare minimum I would expect. After you've researched your top projects, you're going to go through and as a group decide on which project you're going to pursue and further develop. And so when you're deciding on a project, I have some guidelines, some questions that you should be asking yourselves and each other as you're deciding on a project. So once you've gathered more information, you should ask yourself, are you genuinely interested in the application? Is it something that's of remote interest to you? Or is it using concepts that we've learned in class? And I know that can be a little bit difficult because we haven't gone through all of our labs yet. Typically, we would go through all of the labs and then we would start the group projects this semester to try to give the groups more time, especially since it's an online format. We are starting this phase a little bit ahead of time. So again, if you're not sure if a concept's going to be covered, shoot me an email and I can answer that quickly for you. So try to use some concepts from our class and some basic microcontroller commands, but ideally you're incorporating some new code commands and or some new components. And so again, this project is not just to apply what you have learned, but to also encourage a little bit of independent exploration because if you do something similar in your career where you're programming or working with microcontrollers, I can't prepare you with every single possible command that you would ever use or component that you would encounter. But what's important is to introduce you to some of the basics, and then you can apply those to more and more complex commands. So you should be able to have the tools to figure out how to use some of these new commands or how to connect and program some of these new components. So try to add a new element that we haven't explored yet into your project. And then ultimately, this kind of circles back to the third point, but you need to ask, will this challenge you and push your microcontroller skills a little bit? So to speak to this one, I would rather see students try a really ambitious project and get halfway there than to try a super simple project and do it 100% successfully. So by all means, try to pick something that seems achievable, but also pick something that will be a little bit challenging, that you'll really have to take some time to sit and figure out. So I encourage that. I look for that when I'm looking at these projects. Any sort of challenge is always good. It's always going to push you to do better and to explore your new concepts and capabilities. So certainly ask that question when you are choosing a project. Another component to your project that you'll be required to work on this week is a risk assessment. So the specific type of risk assessment that we'll be doing is an FMEA, or a failure mode effects analysis. So this analysis is essentially looking at your project and saying, what could possibly go wrong? What's the likelihood of this? What would it take to resolve? And we'll look at that breakdown in a table in a second. There's a very structured way to set this up that's widely used. And so this method of analysis, as I said, is very structured, very systematic. It's not guesswork. It's not people sitting around a table asking, well, gee, what could go wrong? And then just scribbling out a list. You're essentially scoring every potential failure mode. And so this was developed back in the 1950s by some reliability engineers to study problems that could happen with military systems. So to prevent against those problems and to be sure that they could handle any problems that arose, these engineers came up with this mode of analyzing risk and to help mitigate, to prevent risk, first of all, and to mitigate risk if it did occur. So you'll see this technique. This is widely used in engineering and quality fields. There's a really high chance if you are in engineering right now that you've already used this. If you have a career where you're already performing in an engineering function, or if you haven't yet, there's also a great chance when you begin your career as an engineer of any sort that you will encounter this type of risk assessment or this type of failure mode analysis. This is a really common one used in many, many industries. And so it's typically referred to by its acronym FMEA. Sometimes people pronounce this as FEMA. So if you hear talk about a FEMA document, this is probably what people are referring to. It doesn't quite make sense. They've kind of got the E and the M mixed up, but nonetheless, this is typically referred to as a FEMA, or a failure mode effects analysis. So we'll look at this in a little bit more detail. So this here is a typical FMEA form. If you've ever worked with one of these before, or if you ever do in the future, you will likely see a setup very much like this one. So at the top is just some basic information. What is the product name, or in your case, the project name? Who's responsible for the project, who's working on this form, what's the original date that this was developed, all kind of important information that you would need to reference a particular project. So as we step through the FEMA form, there are some basic information fields that we need to fill out. The first is the process step, or the input. So in a FEMA, we're breaking down different steps in the process and identifying what could go wrong in each step. So the first one is to pick the first process step or input that there could potentially be an issue with. And so there's little prompts kind of underneath these categories. This one is, what is the process, step, change, or failure under investigation? And so we see that we're filling a vessel with water. So something could go wrong here. Something could go wrong with this step. And so the next question is, well, what is the potential failure mode? What could go wrong? And so we're saying that we could get the wrong amount of water. We could fill this up with the wrong amount of water. That's a potential failure. Okay, we've identified the step, we've identified the failure mode, but what does that mean? What are the effects of the failure? What could happen if we use the wrong amount of water? Well, in this case, apparently we're making coffee. So what could go wrong is that the coffee could be too strong or it could be too weak if this isn't prevented. And so we're going to give this a score now on a scale of 1 to 10 of the severity. So 1 meaning it doesn't have a very big impact, 10 meaning it has a significant impact. So if you're a coffee shop, this would be a huge impact. If your coffee is too strong or weak, people are going to judge your coffee, never come back, leave a horrible Yelp review. That could be a big deal. If this is in the context of, you're making coffee at home, the severity is probably much lower. It's probably like a 2 or a 3, depending on how bad you need coffee. So there's no set method for selecting the severity, but you just kind of keep all of the process variables in mind and you pick what severity level seems right to you on a scale of 1 to 10. So now we're digging a little bit deeper into this problem and we're asking, what are the potential causes? So what could cause us to use the wrong amount of water? Well, if the level marks are faded and we can't see those very well, or if they're totally worn off, That could be why we're putting in the wrong amount of water. We could just be guessing. And so then we're scoring the occurrence. So we're saying, okay, what's the likelihood that this potential cause is going to happen? And so, of course, 1 is least likely to occur, 10 means it's extremely likely to occur. And so we're saying it's about a 4. There's a 40% chance that the marks could be too faded to read. And so the next thing we're going to do is look at what are the current controls. So what exists that can prevent or detect this failure? And for this one, we're just saying visual inspection. So just looking to see where the water level's at. And we're saying, so how effective is this mode of detection? This is our third score here. So 1 would mean that the mode is highly effective. 10 would mean this is not very effective at all. And so for visual inspection, we're giving it a 4. We're saying this is pretty effective. This is slightly more effective than not. And so this gives us our total RPN score. Right here, we have a 128. And so if we had some other items populated, we could see how this would compare, and we'll see that in a second. I've put together some other kind of fill in the blanks here so we can see a more complete chart. But so you would want to look at your risk score, and whatever you have in the list that has the highest risk score, that's probably the one you want to start with to figure out how to address it. So this is your initial risk score in this column, your RPN. And so next we have to address it. We can't just leave it and say it's a high risk. We need to say what actions are recommended. So what could we do to prevent this from happening? If our current controls aren't good enough, how can we decrease the likelihood of this kind of bad occurrence happening? And so we could replace any old vessels. We can swap them out, right? Then the marks won't be faded. And so it's easier for us to judge the correct amount of water. And then we're addressing who is responsible. So if we need to perform this action, who's going to do that? We're saying me, which is hopefully the owner of the coffee shop. And then so what were these specific actions taken? So we said that we were going to replace things, but did we actually? We're saying yes, it was replaced on this particular date. So now you can circle back and reevaluate the score. And so this time we have an 8, right? If we have the wrong amount of water, it's still going to be a level 8 severity. But now, because we've replaced everything with new glassware, the likelihood of this happening is only a 1. So instead of a 4, it's only a 1 now, and we're more likely to detect it because the marks are going to have longer to fade. We'll be able to catch them. And so now we have a new risk score. And something I think I failed to mention just a minute ago was that to get your total risk score, you're multiplying the 3 previous values. So you're multiplying severity by the likelihood of the occurrence, by how likely or unlikely you are to detect the issue. So we've rescored everything, and just by replacing the old coffee makers with the new, that's brought our risk down from 128 to just 24. And so when you get this list filled out, you'll be able to see what are your highest risks and what are some quick actions that you can take to reduce the risk. So where does it make sense to invest your effort? So we could get really detailed on this. Like I said, this is used in a variety of places, lots of different processes, lots of different places for almost any industry. But without getting too deep into it, you'll be doing a very basic FMEA for your project. So it's just important to know how to fill in each of these columns. So know what a process step is, know what a failure mode is, what are the effects, kind of have an idea what goes under each of these, and then how to score things. So again, severity 1 to 10. 1 is of low severity, 10 is high, the occurrence 1 is least likely to occur, 10 is most likely to occur, and then detection is a little bit flip-flopped. 1 means you're most likely to detect it, and 10 means that it will go undetected. So if you can't remember, just think which end of the scale is larger. What would make your risk number shoot up? So that's going to be the bad end of the scale. So when we think detection, 10 is going to give us a really high risk score. So of course, if we can't detect it, that's going to increase our risk. So not being able to detect it at all would be a 10, and if it was really easy to catch, it would be a 1. And then we would multiply again our severity, occurrence, and detection scores, and we would get our total RPN number. And then you would just go through what actions you can take to mitigate that risk, and then rescore everything. So here's an FMEA for a car tire. This isn't quite in the little gridded table format as our other, but you can see we're essentially asking the same question. So first we're asking, what is the step in the process that could go wrong? How could this go wrong? How would this fail? What would the impact be? Then we're going to rate the severity. We're going to say, okay, what could cause this failure? How likely is this to occur? And then how likely are we to detect it? And then we'll give that a number. And then we'll come up with our total RPN number. And if I haven't explained this acronym before, RPN is just our risk priority number. As I mentioned, the higher the number, the higher priority that risk should be. So for a car tire, the step in the process we're looking at is our tire function. So can it support the weight of the car with a reasonable amount of traction and provide comfort? We've really gotten really detailed with this process step. So this is one of the functions of a tire. How could it fail? How could it fail to support the weight of the car or provide appropriate traction? Well, we could have a flat tire. That would certainly not support the weight of the car real well. And so what would be the impact? If we got a flat tire, what would happen? Well, it would stop the car's journey. Hopefully, you would stop your car. And then potentially you would be stranded unless you have AAA, in which case you'll probably still essentially be stranded for some period of time. So what would the severity of that be? Well, if you were on your way to a job interview, this would be a really high severity. Family vacation, this would also be severe. And so this is a really high severity. It's a showstopper, right? When you get a flat tire, that's a significant impact on your day. So then we're going to look at the potential causes. What could cause this tire to be flat? Well, there could be a puncture. And there could be some other things, right? So if we thought that there could be an air leak somewhere, then we would create a whole separate line. So these first 4 items would all be the same on the second line, but then we would change our potential cause. So we would have a separate line if there were different causes, or if we were talking about different ways that the tire could fail, we would create separate lines for that. That way we can properly determine our risk mitigation techniques, because the way we prevent punctures will be different from the way that we would prevent a leaky valve or resolve that. So we're saying in this case, a puncture is the potential cause. How likely is this to occur? Not very likely. It's only a 2. So what's our detection mode? How can we determine if there's been a puncture in our tire or not? Well, we can do tire checks before we start a drive. If you notice your steering pulling to one side, that could be an indicator that one of your tires is low. If there's excessive noise, that's usually a pretty good indicator that you have a flat tire. And so how easy is it to detect a flat tire? Well, we scored this a 3. It's not always immediately evident, but usually it's pretty easy to tell when you have a flat tire. And so we're going to multiply all of these up. 10 times 2 times 3. This should be 50. This is certainly not 60. So wherever I borrowed this chart from, their multiplication's a little bit off. But this RPN number should be 50. This would be our risk priority for the tire failing due to a puncture causing a flat tire. So the next step in this would be to say, what are our mitigation tactics? How can we minimize the chances of this event happening? So one of the actions we could do is to carry a spare tire and the tools that we would need to change it. That would be something that wouldn't minimize the risk of getting a puncture in your tire, but it would minimize being stranded because you have a flat tire, which is ultimately what we want to do. So we could say this is a potential solution. This would keep you from being stranded on the side of the road. Well, who should do this? Who should carry the spare tire? Probably the car owner or whoever's driving the car, right? So the car owner, even if they're not driving, should make sure that the car is equipped with a spare tire and any tools that you would need to change it. And then what's the target date? How quickly should this action be performed? Well, you should probably do this immediately, right? If you have a really long trip planned, that's going to be something that's really important. Make sure that you have everything to change a tire. So it would be the ultimate action taken. Well, the car owner would permanently carry a spare tire and the appropriate tools in the trunk. And so now we're looking at what happens. Again, as I mentioned, we're not preventing the occurrence of a flat tire by doing this, so that score is still the same. We're still able to detect a flat tire the same amount. The score for that is the same. What this risk mitigation tactic is doing this time is it's bringing down the severity level. So before we were at a 10, if you get a flat tire, you have nothing to change it, you're on the side of the road, that's a 10 in severity. If you have a spare tire and you can change a tire, then it's not as bad, right? It's still puts a damper on your day potentially, but it does bring the severity down from a 10 all the way to a 4. And so multiplying, again, this last number is off here. Oh, no, it's not. I'm sorry. So 4 times 2 times 3. The last one was correct too. I was adding things. So 4 times 2 is 8. 8 times 3 is 24. And so now we've brought our risk all the way down from 60 to 24. So we've lowered the risk. Something else you could do, right? You could carry like a AAA membership so that your severity would probably be somewhere between 4 and 10. It's not as efficient usually as being able to change a tire yourself, but it's not as bad as being stranded on the side of the road with nothing. So if you had AAA, the severity of a flat tire might be a 6. And so on. So there's different actions you can take here to mitigate this. This is just one. You could put different actions on a separate line of the chart. So this is how we would fill it out. This is just another example of how we would move across our FMEA and go through all these steps. I think I've already covered on this everything on this slide. This just covers what a low number is referencing and what a high number is referencing for the severity, occurrence, and detection rankings. This is just giving you a little, essentially, summary of what each of those are, what a low number would mean and what a high number would mean. It's reminding you to multiply them all together. So I just included this as a quick little reference. When you're filling out your chart, this can help you remember what each of these are and if something needs to be high or low. Here's just another example of an FMEA. This one's for an ATM, and you can see how I was saying you can put things on different lines. Here we had the same process step, the ATM PIN authentication, but we're listing different failure modes. So a lot of times your process, a specific part of your process won't just have one failure mode, it will have multiples. And so you'll want to make sure that you list those all out. And so here they've just noted that everything is all encompassed. Both of these issues refer to ATM PIN authentication. So the failure mode could be unauthorized access or if you fail to authenticate. I'm not going to go through all these. You can take a look at this. But likewise, under dispensing cash, there's multiple things that could go wrong here. And so you could list dispensing cash 3 times if you wanted. You could merge cells. It really doesn't matter as long as you have all the potential failure modes. lined out here, and same thing here, you could duplicate a failure mode. You could have cash not dispersed twice if there are two different potential causes of this. So you would want to make sure that you're listing all of those. So here, if the potential failure mode for not dispensing cash is that the cash is not dispersed, everything else went fine, but the machine just didn't dispense out your cash. The account could be debited, but there would be no cash dispersed, or there could be extra. So that would still be a failure mode. And so something else I want to take a look at here, because now we have multiple lines that we're considering, this is where our RPN number comes into play. So if you'll remember, RPN is our risk severity number, our risk priority number, and this is just a multiplication of all of our severity, occurrence, and detections. And so looking at this, we have a 72 for unauthorized access. The risk of an authentication failure is 75. The risk of cash not being dispersed is 196. And then we have 96 and a 48. So if you are looking at this list of potential risks, everything that could go wrong with a cash withdrawal from an ATM, the thing that you would want to focus on, you wouldn't want to start down here with a lower risk of 48. You would want to say, what is the highest number? What's the highest risk in this chart? What's the highest risk that we can think of? And so by large, that is this, that the cash would not be dispersed, and we're saying that the cause is the ATM is out of cash. So if that happens, there's a high chance of that happening, and a high risk rather. This would be the one that you would really want to focus on mitigating. So what action could we take to prevent this from happening? And so they're just saying increase the minimum threshold limit so that the ATMs could hold more. So you would start at your highest RPN number, and then you would work down. So this first one, where we have 196, this would be your first priority. 96 is the next highest score. This would be your second priority. Then we would have third and fourth, and then this one would be last. So something important to note too, this is getting into the details a little bit, but I still want to cover it. If you have two items where the risk numbers are similar, right, we have a 72 and a 75, so these are pretty close. What you would want to do is say, what are the actions that we could take to prevent these? And then take the faster or the easier action. So 75 is technically a higher risk, but if this is going to take 7 weeks to resolve, if you need 7 weeks to make sure your network is not failing, but to prevent lost or stolen ATM cards, it only takes you 1 week, you should probably work on this one, right? And that's where some judgment comes into play. I would say if your numbers are within 5 or 10 points of each other, you would want to look at this and say, what's some quick actions that we could take to get things knocked off the board if your numbers are close. So you still get to use a little bit of judgment here. The risk numbers are just a little bit of a guideline. Another way that you can assess risk is using a matrix template. And so I've come up with a matrix template here that you'll be using for your project. And so what we have here is the severity versus the likelihood. So before, FMEA accounts for the severity, how likely is it to occur, and how likely are we to detect it. This matrix is a little bit more simple. It only takes into account the likelihood and severity. So if something is acceptable but improbable, it gets a score of 1. It's a low risk. Switch to a different color. If something is tolerable and it's improbable, it gets a score of 4. And so you can see going down this matrix, the further, the more severe things get, the higher the risk score gets. And the higher the likelihood of something occurring, the higher the risk score gets. So if it's a high likelihood and a high severity, that's when you're going to end up with a most extreme score. And so I've noted here the different colors and what they mean. If the at the top, let me switch to my highlighter, our risk rating key. So if a square is green, that means it's a low risk, it's acceptable. If you have a medium risk, so any of these combinations with a 3, 4, or 5 in them, these you would need to take mitigation efforts, determine what those are. If the risk is high, so any of these orange squares, you would want to seek support from a superior, your instructor, something like that. And then if your risk is an extreme risk, so if it's an intolerable risk, it would completely shut down your project and it's possible or probable, that means you should place everything on hold until you get this resolved. So you need to throw all of your resources into this problem to make sure that you're resolving it. Otherwise, it could be pointless to carry on, which you can see makes sense. So if something could result in disaster and is likely to occur, or if you're sure it will occur, you need to drop everything to address that. Um, so this is the risk assessment matrix that you'll be using. I'll cover it again when I review your research and development assignment, but this is a more basic way of assessing risk. And these numbers aren't always the same. The coding is not always the same in these matrices, but you can essentially determine what they mean. So you'll be ranking things based on an X and Y axis, and then you'll have a key at the top that tells you what that final number means. So all you really need to be able to do is pick up here what best describes, draw a line down, and then intersect it with your other variable. And so of course this will be what you end up at. I go up and I find this in the key, or I match the color in the key, and that's my risk. So that's how you use a risk assessment matrix. These can look a little bit different, um, just depending on what matrix you used, who's put it together, but these can be a good quick guideline for assessing a project risk. All right, another piece of your project that you're going to be working on this phase is developing your timeline. So there's a lot of different ways to do this. I'll go over a few. There's no set way that you have to do this, but essentially the purpose of a timeline is to outline who is doing what and when. And so you can see in this Gantt chart, we have person 1, person 2, person 3. We have everyone outlined here. So person 1 is conducting research Tuesday through Saturday on week 1, and person 1, well, we can't see their other task. It must be way out here. But they have a couple different tasks assigned. I think I can see both of person 2's tasks. So person 2 is collecting data Friday through Wednesday. And then so you can see these are piggybacking off of each other a little bit. So person 1 and person 5 are both conducting research together. Person 2 is collecting data in 2 different spots for some reason. These might be different projects. But at any rate, so we're charting out who is doing what when. So you can certainly represent this with kind of a calendar layout and some bars. Another and much simpler way to represent a timeline is just to do a traditional timeline representation with an arrow. And this one is in years. It could be days, it could be weeks. And so under each time period, we're just listing each task that has to be accomplished. The only drawback of this particular example, is that there are no names listed, so these tasks are not assigned to people. What you could do, and what I would recommend doing if you use this type of timeline, is to put the names in parentheses. So for example, we're saying that construction is starting in 2017. This instead could be week 5. And in parentheses, instead of saying that we estimate October 1st, you would just put the name of who this was assigned to. So you can certainly add in the who. We have the what. These are all the what, and we have our when timeline. So you would just need to add a who and potentially put names in parentheses to keep things simple. So this is a simpler view of everything. You don't have to quite so carefully arrange your bar graphs. When you're planning a timeline for your project, it should include a couple things at a minimum. So the first thing your timeline should start with is brainstorming. You've already conducted your brainstorming. So whenever you started that, that's going to be when your timeline starts. So even if something's passed, I still want you to put it on the timeline. And then other things that your timeline should include is sourcing components, if you need to source anything, how much time you need for construction, how much time you're allowing for troubleshooting, and then how much time you're allowing to put together your presentation. So you can really get down into the nitty-gritty details here if you want. If you want to say, write, the first part of the code, write the second part of the code, you can break that out a little bit, especially if you have multiple people working on things. But I'm saying at least at a minimum, your timeline should include these 5 points, and you should have tasks assigned to each teammate for different steps. So not everyone has to do every step, but everyone should have different pieces and they should all fit together neatly. So again, a timeline is who is doing what and when. So that is what you need to make sure that you're defining however you decide to lay out your timeline. I've mentioned sourcing components a couple times in the last lecture or the one before that. I think I outlined all of the existing components that we have at the Kent State campus or at the Tuscarawas campus. There's multiple kits there that have all different types of sensors, so I would certainly start looking at those. Um, use those for inspiration, check if what you need is in those kits. So that's your first step. Check if what you need is already available. If it's not, look for a couple different suppliers and find the best one. So something that's important to consider when you're doing this, if you need something that the university doesn't already have, or if you just want to purchase it on your own, consider the shipping time. So cheaper, if you're saving $10, it doesn't matter if you're receiving the component after the course is over. So please keep an eye on those shipping times. If you need something that the campus doesn't already have, discuss it with me. So send me an email or note it at one of the live Q&A sessions. Let me know what you need. And then send me a link. So if you were emailing me to tell me that you need a certain component, send me a link to that component and a purchase request. And a lot of times the university can actually purchase these for projects. So you don't get to take it home at the end of the course, right? It's university property if they purchase it. But that means you don't have to pay for the components. If you want to pay for the components, you absolutely can. Then you can take them home when you're done. It just depends on how attached you think you will be to the project and to certain components. So if there's something that you need, certainly let me know, and we can work out getting those. Here's the basic risk assessment that I told you that you would be working on for your project. So I'm not making you go through a complete FMEA for your projects, but I do want you to do a basic risk assessment. And so I've given you a little table to fill in where you're just listing the risk. And then what's the severity? How bad would it be if this risk occurred? And how likely is it to occur? So this could be anything from a sensor not working to the circuits not constructed correctly, a bug in the code. Try to be a little bit more specific. Think of risks that specifically apply to your project. But essentially, anything that you think could go wrong should be listed here. And then assign it a severity and a likelihood. So these ones won't be numbers so much because you'll be giving it the severity will be acceptable, tolerable, undesirable, and intolerable. And then your likelihood is improbable, possible, and probable. So you'll want to use this chart to help fill in the table. And then you should also fill in the final risk rating. So whatever number you get here, medium 5 is what you would want to fill in your table. And so I've given you some guidelines as well for whichever risk ratings you arrive at. Anything that's low, you don't really need to worry about too much, right? That's the equivalent of a low risk score. If you have a risk rating that is medium, you should come up with an action plan to minimize the risk. So figure out how can we prevent this from happening, and then ask yourselves, if it happens, what do we do? So if you end up with a medium risk, you'll want to do those things to help your project go smoothly. If you have a risk rating of high, same thing applies. You should still develop controls, create an action plan. It's recommended that you let me know. I can help you work out some risk mitigation tactics and strategies for those. It's not required. You can still just do the controls and action plan on your own if you want. But if you get a risk rating of extreme, and so what that means is that something is intolerable, it will completely ruin your project, and it's possible or probable that it's going to occur, you absolutely must let me know to decide if that's something that we can help reduce the risk, or if you need to select another project. So you'll go through this risk matrix, and I do have little scores in these boxes. So you should have like medium 5 will be your risk number and rating. And then you want to add up your risk score. So add them all up, divide them by the number of risks you have to get your average risk score. And then figure out what rating that would be. So if you end up with an 8, you can look over here in this table and see that 8 is a high risk. If you end up with an average rating of a 5, then overall your project has a medium risk, and so on. So average out your risk score, look at the table to see what that rating would be, and fill in this little bar here at the bottom.